Inflection points. Calculus. Less hungry, more calculus. Oh my goodness. So we've already talked about stationary points of inflection, and I've already hinted about what an inflection point is. An inflection point is where a graph changes concavity. So in an x cubed graph like this, the inflection point is right here, because on the left-hand side of the inflection point, it's concave down. On the right-hand side of the inflection point, it's happy again. It's concave up. So if things are looking up, concave up is happy. If things are looking down, concave down is sad. Happy, sad. Concrete up. You wrote that? Oh. Yes. Maybe Eric's new derivative rules that he's making up will figure out where things are concrete up and concrete down. You never know, right? So we will label concave up in green and concrete down in red, or you can choose whatever color highlighter you would like. And then you can figure out which ones are our points of inflection. So this section, oh, that's not green. There we go. This section here is concave up. This section is concave up. This section is concave up. These sections are concave down. And so that would make points R, Q, and P inflection points. What can you tell me about that point? It is pointy. Okay? At that point, because it's pointy, at that point, it's called a cusp. The derivative will not exist at that point, because you can draw more than one tangent. You can sort of like draw a whole bunch of lines. Well, technically, you can't draw a tangent, but if you think about, I could draw this one that touches it only once, this one that touches it only once. And so since there's more than one possible line that touches it at only one point, at its sharp point. And I guess the way that you can think of it is, what would the tangents look like as you approached from the left? They would look like this. What would you look like if you approached from the right? They would look like something else. Since the left-hand limit and the right-hand limit don't match up, we would say that the tangent does not exist, so the derivative does not exist at that point. There are some, in the homework, there are some very cool questions, I don't know when they come up, but that have cusps in them. So P and Q and R are the inflection points. So we can use the second derivative. Okay, this is where things get confusing for you. We say we can use the second derivative to test for concavity. However, be careful, this is not the second derivative test. What? Isn't that weird how the language works there? Yes. So maybe we should change this word to look for I was like, this always causes confusion. People think this is the second derivative test. No. This is what the second derivative does. The second derivative test finds maximums and minimums. Both the first derivative test and the second derivative test find the same thing in different ways. A derivative is a rate of change of something, right? Because a derivative is slope. Slope is a rate of change of your original function. So it's the rate of change of the rate of change. So if you look at these two graphs that are both concave up, what's happening to the tangent lines? The tangent lines are changing. The tangent lines are increasing. They're getting steeper. As you go from left to right on something that's concave up, your derivative is increasing. So if your derivative is increasing, then you have something that is concave up. Okay? How did we check? Originally, how did we check if a function was increasing? The derivative was? How do we check that? How do we check if our original function was increasing? We did a number line, right? And we drew an arrow up. When did we draw the arrow going up? When it was, you're close, when it was positive, right? If the derivative is positive, we put a plus sign, and then we put an arrow going up. So now, if we want this to be increasing, we're going to plug a number into our second derivative, and if it's positive, it tells us our derivative is increasing, and if our derivative is increasing, it's going to tell us that our original function is concave up. So consider the following. This is what we're going to notice. Here's an x cubed graph, right? On your x cubed graph, you have a maximum and a minimum. So on your first number line, you would have this point and this point, and you would have plugged things in and noticed, oh, plus increasing, minus decreasing, plus increasing again. Okay? Well, here's where the inflection point would be. If you did a number line on this one with that one inflection point, you would find out that your tangent lines here, what are they doing? The slope is going down. This part will be negative. And when you plug it into your second derivative and it's negative, you'll know that it's concave down. And when you plug it into this section, you'll find that it's positive, and this part is all concave up. So what we're going to do is we're going to make a number line. We're probably going to even start labeling our number line with f prime here, because that's our number line for our first derivative. And this one will be our derivative, or our number line for our second derivative. And plugging things into our second derivative tell us how your first derivative is increasing or decreasing, but also tell us about our original function being either concave up or concave down. Similarly, same thing. If your derivatives, if your slopes are decreasing as you go along, you will always have concave down. Look for concavity. Test seems like a better word, but I do want you to put a big asterisk here. This is not the second derivative test. even though that is what your brain would logically think. What does the second derivative do? It looks for concavity. So what should the second derivative test do? Look for concavity. No. To the, well, it looks for max and mins. So it should be the max and min test using second derivative. That would be way better, right? Max and min test using first derivative, max and min test using second derivative. We could, that's too long. Max and min test using first derivative. The MUFT and the max and min test using second derivative, the MUMST. That would be perfect. M&Ms, you just think about chocolates. Yeah. Okay. Okay, but we're not talking about the MUMST right now. We're just focusing on looking for concavity. Okay? So, if your second derivative is bigger than 0 over an interval, then the graph is always concave up. Okay? Again, I always like concave up, and I like to use a plus sign there. Positive, you're happy. Does that make sense? Happy, smiles up. Negative, oh, you're sad. Right? This is the feeling you get when the bell rings at the end of the day and calculus is over. Right? And any time that you change from positive to negative, if the second derivative exists at that point, you will have an inflection point. To show max or min, to show points of inflection, you always need two pieces of information. Okay? You have to show that the second derivative is equal to 0 and it changes from concave up to concave down. That's one way. Or you can show that the second derivative changes at that point, but the first derivative doesn't change. So there's two ways of showing it. Okay. Here's our first question. We want to show that this has a point of inflection. In fact, what we would have here is we would have our first derivative, y prime. We've already done this one, right? 4x cubed minus 12x squared. Now, what's going to naturally happen when you curve sketch is once you find the first derivative, you're going to say, what does the first derivative tell me? Tells me where things are increasing and decreasing, and it tells me where I have maximums and minimums. And so most likely, if you were sketching a curve, you would do more work with this. Okay, I'm going to leave some space so we can do that work after. This question is just saying, you want to find an inflection point. So second derivative would be 12x squared minus 24x. Set that equal to 0, and you would factor out a 12x, leaving you with x minus 2. So solving that, you get x equals 0 and x equals 2. Draw your number line. Label that number line y double prime. Put 0 and 2 on that number line. The nice thing about labeling that number line is it's sort of a reminder. If you're plugging things in to check for positive and negative on this number line, you need to be plugging it in to the second derivative. So something less than 0, -1, I would probably use my factored form. This would be negative. This would be negative. A negative times a negative, this would be positive. What does that tell us? Concave up on the original graph. What does it tell us about the derivative? The derivative is increasing. Second spot, between 0 and 2, plug in 1. This section would be positive now, but this section would still be negative. A positive number times a negative number will be negative. Here we have that it is concave down. And thirdly, above 2, these will both be positive. So, what can we say? Show that it has a point of inflection at 2? Well, at x equals 2, f double prime of 2 is equal to 0, and f of x changes from concave down to concave up. Or, so this is one way to show an inflection point. This is the most common way to show an inflection point because it is the easiest way to show an inflection point. Okay? The other way to show an inflection point would be, and this is why I left the space, if we did our first derivative and set our first derivative equal to 0 and factored out a 4x squared, leaving with x minus 3, we would have got x equals 0 and x equals 3. Drawing our number line here, okay, we would have 0 and 3, and I would label this as y prime, because this is my y prime number line. Plug in something less than 0. Well, this is always going to be positive, that x squared part. But plugging in -2, this will be negative. So this part is negative. I know my graph is decreasing. Plug in something between 0 and 3, like 1. This section's still negative. This is decreasing. Plug in something bigger than 3. They'll both be positive. I know my graph is increasing. And like I said, I think we've graphed this one already. Was it exactly the same? Okay. So this is the one with the bend with the multiplicity of 3 in the original graph. Okay? So the second way to show that it is an inflection point, and the least common way to show that it's an inflection point, is at x equals 2, f double prime of 2 is equal to 0, and f prime of x does not change sign at that point. Doesn't change from positive to negative. So why, like, I find the green one way less intuitive. Okay? So the fact at 2 on our first number line, at 2 the graph is decreasing. and it's continuing to decrease. The only way that that can be an inflection point is that based on the fact that the derivative is 0 and it's not changing, it has to change concavity at that point. Okay? If it changed, you would have a minimum or a maximum. So then it can't be an inflection point at a minimum or maximum. There's no possible way that a minimum or a maximum can change inflection at that point. It's gotta stay. So if you had a graph like x to the 4, the derivative is 4x cubed. The second derivative is 12x squared. Zeros are going to equal all the way through. So you're going to get y double prime is equal to 0 at 0, but you also get y prime equal to 0 at 0. Well, the stationary point, it is equal to 0, so we can't just say the first derivative is also 0. We have to say it changes sign. So even though the first derivative is 0 here, it doesn't change sign on the left side to the right side of it. So it's still an inflection point, and it's a special kind of inflection point. It's a stationary point of inflection. So if you were describing, okay, if something was an inflection point, most likely the blue is what you would do. If you were taking the IB course, every once in a while, they try to throw a trick question at you by using the green knowledge to see if you understood it. But we're not taking the IB course. So I'm happy with the blue explanation. Oh no, IB is very... Okay. So we get our stationary points from our first derivative. We get our inflection points from our second derivative. So when you're sketching a graph, you're going to want to find all your stationary points and all your inflection points, and then you'll be able to graph things very nicely from there. So we start by finding our derivative. This is the technique for graphing using calculus. You find your derivative, 3x squared minus 6x minus 9, set it equal to 0, can factor out a common factor of 3. This factors nicely. So in our first number line, which is our first derivative, we would put on that number line -1 and 3. We know that -1 and 3 are going to be important points. So we need to find out exactly the coordinates of those points. And whenever you're finding a point on your graph, where are you going to plug those numbers into? The original function. Okay? So the thing that gets a little bit confusing, or if you're not paying attention, you could be very tempted, because you're plugging in numbers in lots of different places. You might just plug the number into the wrong equation, because you have now your equation and your derivative equation. But if I want to find my point, I'm going to plug it into my original equation. So plugging in -1, -1, minus 3, -4, plus 9, positive 5, plus 1, 6. Plug in 3. 3 cubed, 27, minus 27. Minus 27 again, plus 1, minus 26. They're not nice looking points, but, well, they are, but they aren't. Yeah, well, it just seems like that 26, -1, 6 seems nice, because your strategic graphing, you're always like from 10 to 10 is the window that you're used to. 26 seems too far away. But it's better than fractions or decimals. So. Yeah, it is. It's definitely that. Yeah, it's online. It's documented now. Yeah. We're gonna, when it goes online, there's probably going to be a warning, not for children under 3, or something like that. Yeah, it could be. That's all right. Okay, so plug a number in less than -1. Let's plug in -2. Go to our factored form because I like using that because it's easy to see if it's positive or negative quickly. Negative times negative. This is positive. First derivative tells us increasing and decreasing. Plug in 0. This is still negative. This one is now positive. That makes this section negative, decreasing. So we now know, using the first derivative test, that -1/6 is a maximum. And when we plug in something bigger than 3, like 5, this section's positive, that section's positive. So it's going up again, and we now know that this is a local minimum. So first of all, we find our stationary points. We find our stationary points by using our first derivative, drawing our number line with our first derivative. Good. Now we need to find our inflection points. Our inflection points are using our second derivative. How do you find your second derivative? You take your first derivative, 3x squared minus 6x. It'll become 6x minus 6. Set your second derivative equal to 0. And solve, and you get x equals 1. So now we can make a number line with our second derivative. We can find the point. It's going to be 1 comma. And if we're going to find the point, we plug it into the original function. So original function, plugging in 1. We'd get 1 minus 3, -2, minus 9, plus 1, -10. So we put only the number 1, plug in something less than 1, plug in 0. That's going to give me negative. Sad. Plug in something bigger than 1. It's going to be positive. Yay, we're happy. Oh. Calculus would have just turned out terrible if they had been the opposite. You wouldn't be able to understand what's going on. But it works out good. Okay. So now, what can we do if we want to sketch this graph? We have the points 3, -26. So when I'm sketching a graph, I'm going to make it to scale as best as possible, but I'll take that worst point, right, again, right, not for kids under the age of 3, that worst point with that -26. Yeah. No, there's only one graph, but they tell us different things. I'm going to label all the points. I'm going to label my minimum there, my maximum at -1, and if this is -26, can you see strategically that +1, oops, no, not strategic enough. Try it again. We're at -1, +6. Yeah, so if this is 26, 6 would probably be about there. We're trying as best as possible. I know this bothers Aiden immensely. If you like, I have graph paper that goes down to like very fine points if you want. Okay.
I'd rather not have an inaccurate graph in the first place.
Okay. So we have those 2 points. You're also going to plug in 1, -10. So 1, -10, I'm going to put that point in as a red point. That would be about here. That's your inflection point. If you can label x-intercepts and y-intercepts easily, you will also do those for sketching your graph. I hope you can easily see the y-intercept. How do you find a y-intercept? Plug in 0 for x into the original graph, and you would get 1 for y. Okay? How would you find the x-intercepts? You'd plug in 0 for y, and unfortunately, you'd have to factor a cubic, which we know how to do, but we put it in as that's a little bit annoying and takes a little bit of time, so we're not going to do it. And in fact, in this one, they both don't work. Nothing works nicely, so you'd have to actually use the cubic formula or a graphing calculator to find it. Then when you go to graph it, we've got our max, we've got our min. Okay? Going to graph this function, I'm going to graph my final graph in purple here. I like to start at my inflection point, because that's where things change concavity. I know that everything here has to be concave down. And everything from this side needs to be concave up. And now we have a really accurate graph. Very accurate. Except for this part where I hit a speck. Went a little bit crazy. So this is what we're going to do for curve sketching. We're going to find all our max and mins. We're going to find all our inflection points. We're going to find all the intercepts we can. We're going to label asymptotes if the graph has asymptotes. And what? Yeah, if it is have an x on the bottom with a non-permissible value, it'll have an asymptote. Okay. So, try this one on your own. The next one we'll do together. The first derivative part. Did you get -1, 1, and 0? Okay. I did my number line underneath here. I'm going to label this as f prime. Did your down ups go the same? Yes. And did you find your 3 points? So save you some time plugging them in. It's not hard to plug them in. Numbers are pretty good. One's a min. I mean, two are mins. One's a max. You don't need to factor this one. You can just isolate the x squared and square root both sides. And when you square root both sides, you have to remember the plus or minus. So your x coordinates of your inflection points are the square root of 1/3. Luckily for us, the mental math is not too bad plugging that into the original equation. But you draw your number line, and I'm going to label this number line in green as f double prime. Now I'm going to save you the mental math of plugging in the square root and tell you they work out nicely to -5/9 both times. Boy, I'm not discriminating very nice because I said very nicely to those points, and I didn't like negative 26 before. So maybe it's just something with negative 26. It's very specific.
Personal like that.
Yeah,
Not just like far away from.
yeah,
I guess that's better than just general
right.
discrimination.
Well, no, this is,
Hate one person because
yeah,
of who they are. It's not okay to hate a group of people because of something.
right. But this is numerism, right? It's numerism. And 26 is not a nice number. Like, yeah, if I was like, hey, welcome to my soccer team, you're number 26, I'm going to quit. It's like double bad luck. It's like 13's good because it's bad, but double 13 is bad because it's good. Oh. Yeah. 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 Please do not get 26% on this test. I will have to attach a drop form. Last step. That's good. So what do we get in the end? Well, when we go to graph this, we label these points. And then I said, well, I should try to find my x-intercepts if it's easy. And this one, it is easy to find your x-intercepts. Because you can factor out an x squared. And it's a beautiful question without any 26s. So it's a wonderful function. We've got e to the negative x cos x on the interval from 0 to 5 pi over 2. Feels like we just upped the level like 15 times in one question. Part A says, find the exact values of the x-intercepts. How do you find x-intercepts? Plug in 0 for y. So I plug in 0 for y, and I try to solve this. It's already factored. It's multiplying, so you can split it, and it's either this part is equal to 0 or this part is equal to 0. Now, how do I know that e to the negative x is never equal to 0? Because I think of its graph. What does an e to the negative x graph look like? Like that. It approaches 0 but never equals 0. It's always positive. However, cos x is equal to 0. Remember, that's your x coordinate on your unit circle at pi over 2, 3 pi over 2, and also 5 pi over 2. Okay? Next, we're going to want to sketch it. Now, we're only sketching it from 0 to 5 pi over 2. So one of the things that you're going to find out is when I give you an interval to sketch on, you also have to draw the endpoints. We already know that one of our endpoints is at 5 pi over 2 comma 0. The other endpoint is when x is 0. If you plug that in, e to the 0 is 1, cos to the 0 is 1, 1 times 1 is 1. So those are our endpoints. Maybe we'll just, yeah. That's where the graph starts and where the graph ends. Now, if we want to find the first two stationary points, well, we have to find our derivative. What do we have to do for derivative of this one? Product rule. Keep one the same. Do the derivative of the other one. Keep the other one the same. do the derivative of the other one. I think I normally, I think I normally keep this one the same first. Sorry. Now, as far as finding a stationary point, we now have to make this equal to 0. And for helping us with that, there is a common factor of e to the negative x. We can factor that out, and once again, that is also never equal to 0. So we just have to figure out where cos x is equal to negative sine x. If you think of your unit circle, is there any point on your unit circle where the coordinates are the same, but one is positive and one is negative? Yes. One's like a root 2 over 2, negative root 2 over 2. That's part of your pi over 4 family. Which quadrants, though? It'll be the second and the fourth one, because you need one to be positive and one to be negative. Okay? Also, if you don't like thinking this way, so you could think this way and think of your unit circle to get 3 pi over 4 and 7 pi over 4. Can you see that I could also play around with this equation, divide both sides by cos, and then I get sine over cos? And sine over cos is equal to tan. And so I could solve where tan x is equal to negative 1 as well. Okay. So 3 pi over 4 and 7 pi over 4 are where it's equal to 0. There would be other points, right? Because you could go multi-times around the unit circle and find other ones, but the question just said find the first two. So we found our first two. Next, we do our number line. Notice the number line this time for my derivative. I'll label it. I included my endpoints because it's going to start at 0 and end at 5 pi over 2. Finding the coordinates of those points, well, I hope that you'd realize that e to the negative 3 pi over 4 is not something you could easily do with mental math. Yeah. We actually get some very tiny numbers, 0.67 negative and negative 0.29 is 0.0029. Yes. Mm-hmm. Chain rule. Derivative of e to the negative x is e to the negative x, then the derivative of the negative x is negative 1. Mm-hmm. All right, are you ready to see the graph? So we plug in 0, 1. We plug in our x-intercepts, pi over 2, 3 pi over 2, and 5 pi over 2. I've got my maximums and minimums labeled in blue. They are very tiny. And there looks like there's an inflection point in there. But we didn't actually figure it out. But I just sort of estimated where it would be.